In today's lesson, we are mastering logarithmic transformations to linear form. In this session, we will transform power and exponential laws into linear form, determine unknown constants using gradient and intercept, and apply these techniques to Cambridge 9709 exam questions. This topic is essential because real-world data rarely follows a straight line. In the Cambridge 9709 Pure Mathematics 1 syllabus, you will frequently encounter questions where you must linearize a curve to find hidden constants. This usually appears as a multi-mark question in the middle of the paper, testing both your logarithmic laws and your coordinate geometry skills. Today, we're looking at logarithmic transformations to linear form. We begin with the power law model, where the variable x is raised to a constant power n. To analyze this, we transform it into the linear form y equals mx plus c. First, we apply the natural logarithm, or ln, to both sides of the equation. Using the product rule for logarithms, we split the right side into a sum. Finally, we use the power rule to bring the exponent n down to the front. On a linear scale, this relationship is a curve. But once we apply the transformation, we can plot it on a logarithmic scale. Now, compare this to the equation of a straight line. In this transformation, the power n directly becomes the gradient, and the log of the leading constant a becomes the vertical intercept. In today's lesson, we'll cover logarithmic transformations. Visually, the power law transformation turns a curve into a straight line. On the left, we see the relationship on a linear scale. It is a curve passing through the origin. By applying logs to both the x and y values, what we call a log-log transformation, the relationship becomes linear. Notice that the gradient of this new line is exactly the power n from our original equation. The intercept on the vertical axis is not a, but the natural log of a. This distinction is vital for your exam accuracy. Let's apply our power law transformation. We know that for the model y equals ax to the n, the linear form is natural log y equals n natural log x plus natural log a. The gradient of the line in the natural log y versus natural log x plane represents our constant n. By calculating the change in y over the change in x using the given points, we find that n equals 2. Now we use the coordinates of 1 point to find the intercept. Substituting the point 2, 3.5, and our value for n, we solve for natural log a. To find a, we must take the exponential of both sides. This gives us a value of approximately 0.607. Always provide your final constants to 3 significant figures, unless the question specifies otherwise. Next, we examine the exponential model. In this case, the variable x is in the exponent rather than the base. This requires a slightly different linear transformation. Again, we apply natural logarithms to both sides. Using the product rule, we separate the terms. Applying the power rule, x moves to the front of the log. Compare this carefully to our straight line equation. The vertical axis y corresponds to natural log of y. The horizontal axis x is simply x. The gradient m is natural log of b, and the vertical intercept is natural log of a. Crucially, note that the horizontal axis is just x, not natural log x. This is a semi-log transformation. If the variable is in the exponent, we only take the log of the dependent variable y to achieve a straight line. A common variation in the Cambridge syllabus uses the base e. Let's look at y equals a times e to the power of kx. Applying natural logs to both sides, we get the natural log of y equals the natural log of a times e to the power of kx. Using log properties, this becomes the natural log of a plus the natural log of e to the power of kx. Using the property that natural log and e are inverse functions, the natural log of e to the power of kx simplifies directly to kx. Comparing this to y equals mx plus c, we can identify our variables and constants. Our vertical axis y is the natural log of y. The horizontal axis x is simply x. The gradient m corresponds to the constant k, and the vertical intercept c is the natural log of a. In this specific form, the constant k in the exponent is exactly the gradient of the straight line. This is the most efficient form to work with because no further calculation is needed for the gradient once you have linearized the equation. Let's solve this real-world style Cambridge question. The variables x and y satisfy the relationship y equals a times b to the power x. The graph of natural log y against x is a straight line passing through 1, 1.40, and 4, 3.35. Find the values of a and b, giving your answers to 2 decimal places. First, we identify the model. It is exponential because x is in the power. We apply our linearization. In this form, the gradient of the line is natural log b. Step 1. Find the gradient m. We use the change in y over the change in x for our coordinates. M equals 1.95 divided by 3, which is 0.65. So natural log b equals 0.65. Step 2. Find b. To find b, we move the natural log to the other side as an exponential. b is approximately 1.9155, which rounds to 1.92 to 2 decimal places. Step 3. Find natural log a using the point 1, 1.40, and our gradient equation. Using the intercept equation, we find natural log a equals 1.40 minus 0.65, which is 0.75. Step 4. Find a. Taking the exponential gives a as e to the power 0.75. This is approximately 2.1170, rounding to 2.12 to 2 decimal places. In Cambridge 9709 examinations, students often lose marks due to avoidable errors in this topic. The most frequent error is misidentifying the horizontal axis. For the power law y equals ax to the n, the horizontal axis must be natural log of x. For the exponential model y equals ab to the x, the horizontal axis is simply x. Always check your graph labels before calculating the gradient. Students often find the intercept value and mistakenly label it as the constant a or a. Remember, the intercept represents the natural log of the constant. You must apply the exponential function, e to the power of the intercept, to find the true value of the constant. Be careful with your algebra. Logarithmic transformation only works on products and powers. If you see an addition inside the original function, like y equals a plus bx, you cannot use these simple log transformations to linearize it. Calculations involving exponentials are very sensitive. If you round your gradient or intercept to 2 decimal places early on, your final values for a and b will be significantly off. Keep the full number in your calculator until the very last step. When preparing for your Pure Mathematics 1 exam, keep these strategies in mind to maximize your marks. Examiners award method marks for correctly identifying the relationship between the gradient of the graph and the constants in the equation. Even if you make a calculation error, writing down ln b equals m can save your score. While you can use base 10 logs, using natural logarithms, denoted as ln, is standard for A-level. It is much more efficient when dealing with the base e, which appears frequently in later chapters like differentiation and integration. If the question gives the model using base e, the gradient of your ln y versus x graph is exactly k. You do not need to take the log of k. However, if the base is a constant b, the gradient is ln b. Read the given formula carefully. In a power law question, the points given are often already the logged values. If the table says ln x and ln y, do not log them again. If the table just says x and y, you must calculate the logs yourself before finding the gradient. It is time to test your understanding. Please pause the video now and attempt these 3 questions. The easy question asks for the gradient of the straight line graph of natural log of y against natural log of x, given the power law y equals k times x cubed. The medium question involves an exponential model. Given the gradient and vertical intercept of the linear graph, find the relationship in the form y equals a e to the power of kx. Finally, the hard question provides 2 points on the line. Use them to calculate the constants a and b to three significant figures for the model y equals a times b to the power of x. Take a moment to solve these before we move on to the solutions. For the easy question, we transform the power law into linear form. The power of x becomes the gradient of the log-log graph. Therefore, the gradient is simply 3. In the medium question, we are given the linear equation. We know the gradient m is k, so k equals 0.4. The intercept is natural log of a, so a is e squared, which is approximately 7.39. For the hard question, we find the gradient using the points 2, 4.6, and 5, 9.1. The gradient natural log of b is 1.5, giving b as 4.48. Substituting back, we find natural log of a is 1.6, giving a as 4.95. First, master the transformation logic. For a power law like y equals x to the n, we use a log-log graph of natural log of y against natural log of x. For exponential models, we use a semi-log graph of natural log of y against x. Second, when interpreting the gradient and intercept, remember that for the linear form natural log of y equals mx plus c, the vertical intercept is always the natural log of the leading constant, such as natural log of a or natural log of capital A. Third, accuracy is absolutely crucial in Cambridge exams. Never round your values for the gradient or intercept mid-calculation. Keep the full precision on your calculator until you reach the final constants. Fourth, for identification, check your axes carefully. If the horizontal axis is x, the model is exponential. If the horizontal axis is natural log of x, you are dealing with a power law. Finally, don't forget the inverse step. Always use the exponential function e to convert your logarithmic intercept back into the original constant required by the question.